Hello everyone, welcome to our presentation with Turkish Aerospace and together with Ingersoll Machine Tools. I am Emre Eriş, I am from Turkish Aerospace, and here my friend Mr. Daniele Martini is from Ingersoll Machine Tools. So I think we are ready to start. Okay. Okay, this is also working. Today we'll be explaining to you our recent project of a multidisciplinary wide and high 3D mold application. It's basically a project that we done for our full-scale demonstrator for an Airbus program. If we just go over our content, so what I will explain together with Mr. Martin is, first I want to give you a Turkish Aerospace introductory film for you to have a better insight of what we are doing. So it's not composed of numbers and figures or how many people we are, but it directly show you what we will manufacture and what we are manufacturing currently. Okay, and then I will show you another animation video of our big investment about composite facility, which give you an idea where we are headed on composite production and how we are committed to be manufactured on aerospace component composites. Okay, then we will have a reminder of our supplier Ingersoll, their capabilities. I think Mr. Martini will explain you during the movie. Then we will explain our motive, why we start this project and what we want to achieve, and what are critical decision points and how we go forward. And of course I will show some pictures of our final product with this project, and then we'll close the presentation. Okay, let's start. Okay, in this video you already saw that all the products that we currently manufacturing, and we are doing it in our on the composite side, our two composite buildings which are almost around 50,000 square meter closed area. And now I will give you our new investment, which is on the construction, and it will be fully operational within 2 years, which is almost 100,000 square meters. Is basically bringing our composite production capacity more than double. Okay.
Turkish Aerospace will have the world's fourth greatest single-roof composite facility with a closed area of 95,000 square meters. This plant will be operated with the highest technology, quality and competence. 2% of the world's aerospace components will be manufactured in this facility. Engineering and development activities will continue concurrently with high-end technological production. High accuracy and productivity will be ensured by using autonomous systems. Augmented reality applications will provide maximum benefit to expert personnel. Turkish Aerospace, having an infrastructure for the Industry 4.0 revolution, will construct a new composite facility as a digital factory. Zero defect will be achieved with high precision equipment. All equipment will be connected to data infrastructure at all times. Productivity and actuals will be controlled with the help of thousands of sensors. With this investment, Turkish Aerospace will greatly increase its production capacity and will contribute to the national economy. Advanced machining and measurement systems will be used for precision. Production will be inspected with ultrasonic and X-ray NDT systems to ensure quality for assembly. All supported paint shop will control autonomous finishing operations and key process parameters. We know that the future is in the heavens. We are moving fast with our goals for the country's economy, technology and development. Turkish aerospace industry. Our eyes are in the sky.
Okay, so this is where we are heading, and we will be making this fully operational within 2 years. So we can continue with a reminder of the capabilities of our supplier Ingersoll.
So thank you everybody. As Ingersoll, we are in the north of US, nearby Chicago, and it's been an honor for us to cooperate with the TAI to open a new frontier in the field of molds. Actually, Ingersoll is very much used to open new frontiers, as you see from this very short movie, giving you some ideas about our last experiences and innovations that we applied. Has been in some way limited this movie to the composite field, but Ingersoll has been born 1 century ago for metal cutting, so we have a lot to say, we have a lot to do. We are not going to go into detail on any of this stuff. We have to go into detail about the job done together with the TAI and reaching results that you will see within minutes. And we are really proud about these results. Everything is based on what we see just now, that is 3D printing. In this case has been done basically with a robotic solution with a limited dimension of the parts. But this machine has a much bigger parts, and this is the machine that has been applied for the TAI experience. We are, for your information, exhibiting in Hall 5 and 64, and we have two interesting aerospace molds. They are not from TAI, but they are interesting to see. They are quite big. The solar telescope is our really end effect. We are very proud to be into the solar experience, let's say, with one of the most gigantic, accurate machinery ever done in the world.
Okay, now we are complete our introduction actually. Now I will start about giving you more details about the project. So please remember, I am the composite production manager of Turkish Aerospace, and when we start this project, I was the industrial lead of these composite parts. So what I will tell you is the direct view of a aircraft part manufacturer. Okay. So, as Turkish Aerospace, we are awarded for Airbus single-aisle Neo fan call program. So this is basically the part we will deliver in the end. So we got this project as a design and build program at August 2017. Okay. As soon as we got the project, we start our manufacturing trials, of course in a subscale, because we don't have a that big tool. And in the end, this is our production method. We will have fully panel fiber placement, and we will make our omegas procured. Then we'll make a co-bonded structure. As you can see here, it is an almost 4-meter arc, so it's a really big part, and it is almost 1.5 meter wide. So with these omegas and this size part is a really challenge if you consider it's then hollow structure. So, for serial production tools and for test units, we have already given our decision to go with in-var tooling because our rate is really too much. So we have to manufacture 120 of these panels per month. So it has to be in-var. But to give some information for in-var, before we start in-var tooling manufacturing, we have to collect some data. So we need a full-scale trial. So just assume we will need a layup tool. We will need a layup tool for omegas. We have to have a curing mold. These two can be same basically. And with achieving this full-scale demonstrator production, we can have manufacturing feedback and also full-scale concept approval. That's the target. And our main objective for a full-scale demonstrator is basically these three items: to understand difficulties of part production one-on-one scale, because in the end we are the part production and manufacturer, and we have to make 120 of these. We have to verify our production time estimation, to calculate our rate and ramp up to catch up with Airbus schedule, and also we target to gather information from cured parts to support our forward manufacturing actions. And for demonstrator tooling, these items, it has to be short production time, relative low price, precise geometric features, and has to withstand up to 10 cycles to support our manufacturing trials, and has to be easily reworkable because it's a full-scale demonstrator tool. Okay? And we check out our options. Of course, we can do this with several ways. The first way is, of course, metallic tooling. So these are the main steps for manufacturing a metallic tool. We can use a carbon tooling, which we will construct first a seafoam or foam model, and then we'll complete layup on this model and make the tool. So that's the second option, and this is the third option.
What we see now is our demo master print machine is installed in Rockford, Illinois. Is at the disposal of any client for a demo, a testing with various material. This very moment, the machine is producing the female tool for TAI. As you see, is quite a large part. Actually, the machine has a capability of 12 meters long, so it's prepared not only for aerospace, also for nautical and some other applications. This is a machine with a present 200 pounds per hour production capability. We are already waiting for the 500 pounds per hour extruder. The very high peculiarity of the machine is integrated with a 5-axis milling operation that can be easily replaced on board of the machine, so that keeping the part in the same location, we get a finishing of the noble side of the part. Very nice. The machine is running Siemens 840D, the industrial standard.
This simplicity you can manufacture tool, and actually you can see here we have already done that. Okay, so we collect our options, and this is a really important decision point for us to go which way. So if we just maybe go over the variables here, or the major variables, you can see the cost of INVAR is of course too much according to other options. So at the beginning we think of a high temperature tool that can put in the autoclave, so it is actually that's relative price. And remember this, these prices are according to our own experience and according to our local suppliers, which are really good in tool production. So I believe if you try to do this in States or Europe, these INVAR steel aluminum tool prices will be even higher, okay? And for durability, as I explained in the beginning, we need 10-15 cycles for this full-scale demonstrator. And this 3D printed tool is also covering that. By means of geometric features, it is really doesn't make much difference, because we are machining every tool with a 5-axis machine. And when we talk about reworkability, 3D print tool is really far away from them. I will just give you some examples about it. But with 3D printing tool, we have one disadvantage, which is the thermal expansion coefficient. With this size and this geometry, the thermal expansion of our material, PPSU material in the autoclave, is not proven, okay? Because the part geometry is really unpredictable. But we have to give a decision and we have to go forward. And for this decision, we consider two main aspects, okay, making our decision. First one is we have to achieve a full-scale component to support our customer in the industrialization phase. And the second motive is, of course, we want to be a leader in this technology. We can use it for our own indigenous programs, and we can be a reliable supplier to OEMs for this service. Currently, we have already achieved to manufacture an ABS mold to replace the foam. So we go with a hybrid solution. We replace the foam with an ABS mold, and we'll generate a carbon tool from them. And we have manufactured our layup mold, that what you saw in the movie, to support our production activities. And for PPS mold, we are planning to achieve this in the second half of 2019. Will be this tool in hand in TAI, and we'll put it in autoclave, see the results, and it will also decrease the overall time. Now, this is our studies, that steps we complete at Rockford with Ingersoll to have these tools in hand. So you can see this our base model. so it has a lot of structures and closed loops inside. But we see that when we do too many loops, okay, too many loops and too many discontinuities, we saw there are some thickness variations and this kind of imperfections. So as you remember, I told that it is really easy to change and adapt a 3D printing tool. So we saw this in the morning. We just want to see how it goes to the night, and we saw it is not working. We changed the model to this cross section. Okay, this is just a trial cross section. You see, we just bring infrastructure like cross here. A question occurred, I am sure. So it seems really weak. Okay, and it's ABS. Does it really weak or not? Let me show you. This is my friend. He's 75 kilograms, more or less. And this is a 3-layer print, okay? Now I am lifting on other end. You see, it is really strong. And it's getting weirder. So now he step in between. They are 2 layers. And still standing. So it's a really good way to manufacture. It can withstand force, no problem.
I have to add an information. It's not a pure ABS. It's ABS carbon charged, 25% short fibers into the carbon, into the ABS. This is just one of the various, I should say, really a lot of possibilities to apply. But what Emre just showed is giving you an idea how solid are these kind of artifacts. Meaning that not only using a lot of material, in this case to make a mold, but also using much less material to make parts. Maybe not aerospace grade, but a lot of other fields can be solved by this kind of approach.
Okay, so now this one is the final model that we achieved, and this is like at the end of 4th day, okay? So we changed several times. We optimized within 4 days the design of the tool, okay? And you can see it's completed, and after machining, we have received tool in our facilities. So this is our clean room. We got the tool, layup tool, and this is our male mold that we'll use instead of foam model, okay? There's a Turkish flag here because I have to hide an aircraft part after that, okay? And we load the tool, our existing AFP machines. We make the layup trials already. So what we designed, what we manufacture is working with our current system as we predicted. So the tool manufacturing overall seems to be very reliable and predictable in the end. So it's working. Of course, meanwhile, with the layup, AFP layup, we constructed or we manufactured our autoclave tool. Okay, this is basically steps. And of course, we have to do same step for our omegas, and this is our finalized carbon tool for omega. It just go in the same way. We have a matching surface 3D printed already in-house. We generate our tools, and you can see bottom, we already cured the parts. No problem. So this is the completed layup. It's a picture from our clean room. We complete layup, we located the omegas in place, and this is the cured part. Okay, this is done. It's in our facilities right now. So, to sum up, I can tell you we have our short production time target is achieved. Our relative low price target is achieved. Our precise geometric features are achieved. And as you can see, we really and easily play with this tool, change its abilities, and even we scrap one, we can just build another within 2 days. Only question remaining is about this high temperature autoclave usable tool, and as I said, we are working on that. So, if we think a little bit widely for aerospace applications or any other application. So we can really say, we are really confident that this process is ready for large scale. This is a really, really big tool you see on the AFP machine. Process is really ready for any low temperature application, like mill fixtures, check tools, maybe some assembly jig applications. But we have to process the high temperature application, and we have to prove this. And I will show you one example of how it can be used. So this is a mill fixture from our facilities. Now we are using it for serial production. I am sure you see the resemblance. It's basically the same tool, but metallic. From tomorrow, we can change it to 3D printed. And I can tell you that with the price, it will be almost 25% if we go with 3D printing. And production time, it is less than 1/3 of the tool. And that's actually more or less what I want to say. How we can use this technology, how far we go, and how close we are to apply it to full extent of the production. And now I will leave Mr. Martani for the final words.
Yeah, as already introduced, this machine is for everybody to improve the knowledge about capabilities. Is a really nice toy to play with. A bigger point of our machine, our technology, is that we use materials from the end user, in a pellet way. So we start from simple pellets, any material thermoplastic in a range of temperature, but we can reach up to 350 degrees in extrusion. And as you see, we have room enough for any kind of application. Now, talking a little bit about high-grade thermoplastic in order to apply in autoclave, we already perform a lot of testing with another client, American client, and the size matters a lot. So we have already working solutions in autoclave using a PESU or some other kind of thermoplastic for higher performances thermoplastic. What we tested and qualified are molds up to 1.2 meters by 0.8 meters of size. Definitely the mold that we are talking now is much bigger. So even testing this mold means to put down 1 ton of material and then go to autoclave. So the testing is much more challenging and expensive, if you like. But we are really, really confident that even in this kind of size and in this kind of geometry, because even geometry is changing the game, but even with this kind of application, we will reach finally the results that are in line with the expectation of the clients. I say the expectation of the clients because every client has different expectations. Aerospace is looking for, let's say, 0.05 millimeters of accuracies. The accuracies in nautical are probably 50 times wider. So it's really a new era that is opening to the large scale parts too. So far the 3D printing has been developing and very well known for producing laboratory stuff or something for artists or designers. We really believe that very soon the 3D printing in an industrial size will flow into the market, opening really new frontiers. Don't forget that 3D printing is even ecological. Why? Because there is practically no scrap there. When you consider a lot of other kind of technologies, there is a lot of waste material during each passage. this kind of part in this very moment has no scrap at all, and after the finishing operation probably the scrap will be 2%. So this is another good point for our future.
Okay, thanks for your attention, and we are happy to take any questions.